Yeah, so I'm going to give a talk called Dimensional Reduction to Droplets, Understanding First Order Phase Transitions. And I was asked to give kind of a review talk. And so this will be a little bit of a review, but it's a little bit experimental in the sense that I'm trying to select some of my favorite things from kind of all the different stages of this so-called pipeline that Ollie talked about in the last talk. So let's get started. But if you, by the way, want to play along at home, you can go to this URL, this web page, or else check out, go to the Indico and click on the material, and you can follow the slides and the movies and stuff there. And all the references are hyperlinks within the slides, so you can dig deeper on your own if you want, or skip ahead. But yeah, let me just start with this slide from a really nice simulation that my now postdoc Daniel Cutting made from a simulation of a strong first order phase transition a while ago. And you can see this is temperature, so redder bits are hotter. And in some sense, the black lines correspond to the bubble walls as the bubbles are emerging. And you can see these regions which are very hot, which are not really spherical, but are kind of starting to become more spherical as the bubbles merge in the symmetric phase away from as these start to collide. These hot red areas are so-called shrinking droplets, and they're the thing I want to focus on at the end of my talk. But I want to kind of take you back to the start of the pipeline, this kind of analysis pipeline that we talk about, and ask how do droplets form and what are the consequences of gravitational waves. And in order to understand that, we need to begin with a particle physics model, which I'm going to follow up on what Ollie was saying, and I'm going to talk a little bit about how one would use dimensional reduction to make that easier to study non-perturbatively, and then get phase transition parameters from that, which we can then use as input to or matching for cosmological simulations, which then gives us a meaningful prediction for the cosmological gravitational wave background. And there are some key parameters which bridge this gap in the middle, like this kind of central keystone of this analysis chain, which includes some measure of the phase transition strength, which has various particular definitions, but it's generally denoted alpha. And then how long the phase transition takes to complete, which again, you can measure in various ways, but the kind of leading order contribution comes from how long is kind of like the tangent to the nucleation rate, which one can measure with the inverse phase transition duration. And then there's a couple of temperatures, and one of those might, for example, be the nucleation temperature, which you're release getting one bubble per Higgs volume starting to nucleate. But these are again a purely partial selection of these parameters. And this does form a so-called pipeline stretching off from one end to the other, of which these are kind of the central element. So let me just, thinking about this pipeline, let's just look at the upstream parts of it first, and talk about how to get from a particle physics model to phase transition parameters, and then come back to the other stuff a bit later on. So again, we might have talks during this workshop about, for example, phase transitions happening in dark sectors, or the QCD scale or somewhere else. But my focus, just for concreteness today, is extensions of the standard model. So in that case, our original four-dimensional Lagrangian is something which consists of the standard model fields and then some BSM contribution, which could itself just be some higher dimensional operators, but could equally well include new fields beyond the standard model as well. So as Ollie was talking about, for example, singlets, or as I will come back to later, for example, a triplet as well. Could be examples of extra fields which give you interesting physics there. And that's the sort of thing that I want to certainly consider here. So what is the electroweak phase transition? Well, it's the process in which the Higgs turned on. So we have some way by which the Higgs goes from the kind of false vacuum through to the true vacuum, and this in the standard model is not a phase transition at all. Actually, it's a crossover. But there are many extensions of the standard model, some of which we have already discussed or mentioned, and which members of this workshop work on themselves, in which it is first order, and in which case there would be some contribution from those colliding bubbles and what happens after that. which makes gravitational waves. There are, of course, other very interesting consequences of electric phase transition being first order. For example, the viability of baryogenesis in standard kind of mainstream electric baryogenesis depends on it as well, for example. But from the point of view of this workshop, the observable signal which we're interested in, other than there being more matter than antimatter or other interesting consequences, is whether they produce gravitational waves or not. So that's what I'm going to focus on for the time being here today. So yeah, so then just kind of thinking very naively and straightforwardly about the standard model, this is kind of one of the great successes of kind of DSM phenomenology of the 1990s, was finding this phase diagram for the minimal standard model, by which I mean no extra physics beyond the Higgs. And so what you have is you have a phase diagram which has, in terms of the Higgs mass, there's a line of first order phase transitions which goes up to around about 75 GeV, and then beyond that you don't have a phase transition at all. The system would proceed through a crossover, and on the y-axis here we have temperature, and the endpoint there, that 75-ish GeV endpoint, is a second order critical point which has the same universality in this model. So we have this kind of very standard electric phase diagram, which was very, I said, was a very impressive result using non-perturbative techniques in the 1990s, and in particular relies on a technique which we call dimensional reduction. And in dimensional reduction, as Ollie already mentioned, and I'm just going to quickly run through again just now, you take advantage of the fact that in thermal field theory, at large distances, much larger than the inverse temperature scale in the model, the system looks essentially three-dimensional. And that's kind of the way, if you're making a t-shirt about dimensional reduction, that's what you put on the front of it. It's a little bit more subtle than that, of course. And in particular, one of the reasons why it's interesting for the point of view of looking at physics beyond the standard model is that if we have a phase transition where masses get very small, then you have the infrared problem that Ollie alluded to, that the expansion parameter becomes very large, this Linde infrared problem. And so therefore you want to have a way in which you can deal with those in the kind of infrared physics modes without having to also handle the fermions and other fields which don't have to be treated as light fields. So that's one reason why you might want to use dimensional reduction. But in order to get from the full four-dimensional theory down to three-dimensional theory, you have to basically order by order match Green's functions in the four-dimensional theory to the equivalent Green's functions in three-dimensional theory to the desired order. So this is not a trivial thing, and itself is very impressive. And it doesn't necessarily mean you have to study the resulting theory on the lattice. You could also use three-dimensional perturbation theory to study that as well, as I'll briefly come back to again later. So this dimensional reduction is a very powerful technique. And again, I want to emphasize that dimensional reduction is a pair of words which appears regularly in other areas of physics as well. I think, for example, in other areas of theoretical physics, we also talk about dimensional reduction, but they shouldn't be confused with the technology developed for thermal field theory, which is what I'm specifically talking about here. It's just unfortunate that we have so many, only so many words to describe different physical phenomena. But okay, so then you have a dimensional reduced theory, and what was developed in the 1990s in the paper linked here is a 3D theory of the standard model, minimal standard model, which you can then simulate on the lattice. And what you can then do is because the minimal standard model, the Higgs potential just has basically a quartic and a quadratic parameters, we can write them as basically x and y, so two-dimensional parameters here. So you can map the kind of the full four-dimensional phase diagram onto a three-dimensional theory phase diagram with these x and y parameters. And in terms of this x parameter, which is the dimensionless quartic coupling, the endpoint of the first order line is about 0.11, and the critical line in terms of the squared quadratic coupling is about y0. So that's all well and good, and you can, as long as you can match back to the 4D physics, you can then say that if you have a 125 GeV Higgs boson, as we actually do, then it would be a crossover. But there's another thing you can actually do, which is that, as we noted briefly when I was looking at the kind of the hierarchy of scales and dimensional reduction here, if the physics, the additional physics you have is not new light physics, you can just integrate this out and actually map it onto the same phase diagram as we have here on the right. So we can actually just use that, get rid of that additional field if they're heavy enough not to be treated as dynamical fields, and use this existing three-dimensional phase diagram to study the new physics. And so that's what we did in this paper here. And so here you have, this is a contour plot, and there's quite a lot going on here, so I'll just take some time to explain what's going on. So on the x-axis here, we have the phase transition strength. So this is this alpha, and then the y direction, the y-axis, we have the inverse phase transition duration, beta. And we also have some contours of signal to noise ratio at the bottom right for Lisa, which might come back to later. But the thing I want to focus on here is that every heavy every theory basically of physics which contains additional heavy fields, which you can map onto the same three-dimensional theory, lies in this blue rhombus that you can see here, basically. So this kind of blue region here is all the theories which contains all the theories of heavy physics beyond the standard model, which can be integrated out in dimensional reduction. The other thing you can see here is a benchmark point. So the NP here shows if you study the physics of some BSM theory with extra heavy physics with the lattice simulations, then 3D here is if you do perturbation theory after having done dimensional reduction. And then the 4D point here is if you do just standard 4D perturbation theory. And the thing to bear in mind here is that the 4D perturbation theory underestimates the strength of the transition, so the x-axis. It's about almost an order of magnitude, it's certainly a factor of 5 away from the actual strength of the transition seen in lattice simulations in the 3D scenario, as well as a little bit away in nucleation rate. That can vary. For example, some of the scenarios that Ollie presented in his previous talk, it was actually such that the inverse phase transition duration's beta parameter also had large theoretical uncertainties. But it was plots like this which I think got us thinking a little bit about whether one should try to kind of understand how accurate perturbation theory is in terms of predicting these phase transition parameters, given that it seems that 4D perturbation theory is so far away from the non-perturbative result for this benchmark parameter choice. So there's some interest. This is kind of already food for thought in this paper as to how accurate you can be. But if you have heavy physics, you're stuck in this kind of rhombus of misery here, and you're kind of well away from the region where you can get an observable signal noise ratio with Lisa. And so in order to escape this 3D standard model like effective field theory rhombus that I shaded gray this time in this plot, you can go in any of the 4 directions. But to get towards stronger phase transitions and in principle observable signal at Lisa, then you basically have to do one of 2 things. Either you have to add higher dimensional operators, or you have to add additional light fields. Those are the only 2 things you can really do in order to get that way. There's other things which people often do when they're thinking about these models, but in practice, to get towards the direction that you want to go in, which is basically making X so small that it's the theory that is no longer self-consistent. When you just have this simple quartic model, you need to have additional BSM degrees of freedom or dimension 6 operators. Okay, so I just want to give another example. This is a slightly more recent paper with Michael Ramsey-Musov and Lauri Niemi. And in this, and Thomas Tenkinen, and in this, we look at the kind of how well you can predict the phase transition parameters using, these are lattice simulations, the points, for a triplet extended standard model. So this is the minimal standard model, but rather than integrating out all the new physics, we've kept a dynamical triplet during the dimensional reduction and then simulated the whole theory on the lattice non-perturbatively. And so on the x-axis here, we have temperature, and we've chosen 2 benchmark phase transition points. And this theory has what we call a 2-step phase transition. So it goes through a phase transition for the sigma field and then for the Higgs field as we go to lower and lower temperatures. And what you can see is that the benchmark point on the left has a crossover. Basically, the blue points show the Higgs the triplet condensate smoothly turns on from 0 and goes to a number and then jumps back to 0. And that smooth turn on is indicative of a crossover. And if it persists in what we call the continuum limit, which it does in this theory, in these simulations, then it's a real thing. And then after that, when the triplet condensate jumps back to 0, the actual Higgs phase transition, electroweak phase transition occurs, and we jump. The Higgs rev jumps. Higgs condensate jumps to about 2.5 or so. This is I'm talking about the left plot here. And the things to point out here is that the temperatures at which these 2 phase transitions happen are by as much as 5 to 10 GeV. And the strength of them is, well, firstly, the perturbation theory doesn't even know the difference between a crossover and a phase transition. It doesn't know what to do. So you have to kind of, that's something you have to put in by hand as kind of an external parameter. You can't say whether it's a first order phase transition or not. But supposing that we ignore the fact that it doesn't know that there's a crossover, it still gets the strength of the phase transition, which we can kind of measure by the jump in these condensates, wrong again by as much as 10 or more %. So there's some clear uncertainties. And on the right here, we can see something which is even more severe in terms of getting the kind of critical temperature and also the order of the phase transition quite wrong. So these benchmark points in the triplet model show you that basically perturbation theory, you can't see the phase transition and it gets some of the key phase transition parameters quite wrong, which is why I think it's not just me, but you've heard other speakers and you might hear other speakers still talking about the importance of using non-perturbative methods, or at least alternative methods to the standard 4-dimensional perturbation theory of BSM phenomenology to predict these parameters for phase transitions. All right, so what are the key points so far? What have I tried to tell you? I've tried to tell you that dimensional reduction and lattice simulations are, since the 1990s, a very well proven method for studying these BSM theories. They are kind of the gold standard in some sense. And I've also tried to tell you that if you have heavy new physics and you don't include new operators, then you're trapped in a sort of rhombus of shame far from the observable area for LISA, or other future gravitational wave missions. You need light new physics or higher dimensional operators to get a strong phase transition, which is observable at gravitational wave detectors. And I've also tried to persuade you that it's important to benchmark perturbation theory results, either by using alternative perturbative calculations, as we've already seen by Ollie and others, or by using lattice simulations, as I mentioned briefly there. But okay, let's say that I persuaded you of that, and so now you've got some parameters, alpha, beta, nucleation temperature, such like that give you a nice strong transition. You're well into what you think is an observable region for future gravitational wave missions, and you want to simulate it. All right, well let's try that, shall we? So just a recap of how these what we do when we're simulating these kind of these scenarios. I don't want to go into details again. I tried to make this talk a little bit different from the other talks that you might hear today. We've already had a really lovely introduction from Chiara about how you go about doing these simulations and how you compute gravitational wave signals from them. So instead, I want to just briefly summarize what happens there. So we have, in principle, if we're simulating the whole scenario from end to end, we nucleate bubbles, or nucleate them by putting in some blob of expanding blob of scalar field. And as it expands, and assuming it experiences friction, we have also heard earlier today that it doesn't necessarily need to experience friction, but presuming that it does in this simple model, then you'll get a reaction front around it, which will either be a detonation of some kind or a deflagration. And as these bubbles expand, eventually they'll start colliding with their neighbors. And then after that, after the collisions have completed, if they complete, we saw some droplets at the start, and we'll be coming back to the droplets in just a few slides. Presuming that they complete and everything goes smoothly, then you have sound waves left behind after that, which soars gravitational waves quite linearly and quite happily and quite sedately for a while. And after that, in principle, you can get shocks forming after a while due to this being a hydrodynamic system with some viscosity, and we've given length scales, and that then leads to a cascade, which then could lead to turbulence, and eventually you might get either damping from viscous damping, or more likely the Hubble damping will expand and dilute it out of existence. So there's a sort of again, this is what you put on a t-shirt if you were doing this for a living, I think. And there's 3 stages here which produce gravitational waves. The initial collisions of the bubbles, and also potentially the reaction fronts, the production of the sound waves, and the sound waves kind of piling on top of each other, and then potentially again, a motion of the plasma, but a more turbulent motion of the plasma, or a more shocking motion of the plasma later on. And so these kind of 3 areas, depending on the exact detail of the scenario, are where kind of the most theoretical work on these simulations and theoretical understanding of the gravitational wave signal comes from. And they all have kind of they're all separately studied by different groups in different times. But I want to focus on the sound waves for the time being, because that's what works very well for weak transitions. If alpha is pretty small, then everything is quite linear. And these simulations that we did of basically sound wave collisions from gravitational waves back in 2017, here you can see some the gray and black curves, which are some scaled by time, and show you that they're basically a stationary source of gravitational waves, while the sound waves are continually sourcing stuff. And also you can see here that there's a red line, and that red line is a broken power law that was first postulated in a Lisa Cosmology Working Group paper, and which we kind of put to the test in these large-scale simulations here. And those results kind of check out that it's not perfect, but this ansatz is better than nothing in terms of describing what this source looks like. And it's also pretty well described in slightly more detail. Again, it's not perfect, but it's pretty well described by Mark Hindmarsh's sound shell model, which again is assuming that these sound waves basically are superposable shells of stress energy of the right shape, which then source gravitational waves for a time. So weak transitions, I think, I'm not saying that they're an open and shut case, but they're certainly well understood. And they're kind of our presumptions and expectations for how gravitational wave power spectra look for phase transitions are inspired mainly by these simulations that we've carried out of weak first order phase transitions so far. And just as a little advertisement, you can explore these predictions with this pt-plot.org webpage, which will let you put these parameters into the webpage, or else explore benchmark points from one of the Lisa Cosmology Working Group papers. And here I've chosen actually these points, these blue points on this plot here, are for a parameter space scan of a Z2 symmetric singlet extended standard model set of benchmark points by Jonathan Kozaczuk and collaborators, which are summarized in the Cosmology Working Group paper here. And again, you can see here that this is on the familiar alpha and beta axes. You can also notice the nice kind of sudden curve backwards in the upper part of the plot. The gray region here is actually where expansion happens before the source becomes shocky, and the unshaded region is where the shocks will happen before, and then potentially turbulence will happen before the system dilutes out of existence. So in line with what we've observed and also what has been put in the more sturdy footing by Marek, Josemi, and John Ellis and collaborators. We conservatively turn off the signal at one shock formation time, just again, on dimensional analysis grounds. We can't trust the sound source that's after that. So this is a conservative estimate of what you could see, what points can be excluded in this singlet extended standard model here. So that's the sort of thing that you can do with PT plot. Okay, so weak transitions are fairly well understood. Again, there's some dotting of I's and crossing of T's to still do, but there's plenty more than just weak transitions that happen. And especially these days, I think theoretically a lot of us are very interested in particularly strong transitions, perhaps motivated by supersymmetry or by conformal extensions of the standard model and things like that. And then the question is, what happens if you have a thermal phase transition in one of these models? And clearly it's not a very linear thing. So we'll probably have some nonlinearities developing during the transition. And so one thing which might happen is that, and we might see it, you can even see it hinted at in the background of this slide, is that things will get vortical. So you'll have generation of vorticity during the transition itself. We'll also, as I foreshadowed, get droplets as well. But equally well, because we have this time scale in which shocks and turbulence form, then we can easily see nonlinearities forming after the transition. And Chiara talked a bit about our own explorations of the onset of these nonlinear behavior. And I think Alberto will tell you a bit more about the Nordita group's work with Pencil in trying to simulate the onset of turbulence in their own code. So leaving the nonlinearities after the transition to my collaborators and friends, and I'm going to talk a little bit more about droplets, because droplets were my title, and it rhymes with the two D's in the title rhyme. So let's look at droplets. And before we get onto that, I want to show you a movie from which some of these stills are extracted. This is a relatively strong transition with a relatively slow deflagration. And this is the velocity, 3 velocity field V, the magnitude of it. And this is a movie made by Daniel Cutting here with our code. And the white is the boundary, short the boundary of the bubbles. So this is basically the Higgs field wall. And the brighter the colors are, the more velocity there is. And you can see that basically the walls slow down before they start to merge. So there's these fairly long-lived regions here. This is velocity, not temperature, so it's a bit hard to see what's happening inside the droplets, but they, rest assured, are heating up before they eventually collapse. But the walls do really slow down there. I think you might agree. And you see also this generation of vorticity that I mentioned here and foreshadowed in the previous page. Stuff isn't very linear anymore. You can see why the sound shell model probably doesn't work here anymore. Things are not just moving as sound waves through the system anymore. So this is a bit different from that. I'm just going to run that movie one more time. So again, watch the white curves there, which are where the bubble walls are, and see that it's a little bit hard because the frame rate on Zoom is a bit low. But you can also check it out on your own laptop later, or go to one of our web pages or something. But you can see that here, like the walls are slowing down and the bubbles are no longer quite spherical. And this is due to this heating in front of the bubble walls and the formation of droplets as we go, basically. Like so. I'll just let this run through to completion one more time. So you've got a few spots there where things are taking their time.
David, it's 5 minutes left.
Yes, thank you. Yeah, I'll be on time. Yeah, and there is our droplet going there. Cool. So let's let's get a radar gun and point our radar gun at the bubble walls and see how fast they're going. So we use some proxy measure in these lattice simulations of the wall velocity. And so here's a plot of our estimated wall velocity against time for simulations like this. And as the color gets brighter, as we go up in alpha, the phase transition is getting stronger. And so the case you just saw in the movie is the bottom, which I see as a lime green yellow color here. And you can see here that, again, this is just a proxy. So this is not an actual measure of the wall velocity itself. It's a proxy of it. So it's not without bias, but you can see here that at late times in the strongest transition, the walls basically slow down and stop. Whereas, for example, in the weakest case, so the alpha 0.05, the walls accelerate and then basically disappear very quickly. Yes, they do kind of reach maybe an asymptotic velocity or something, but it's very short-lived, and the region of uncollided volume is very small. So basically, this is evidence that the walls are slowing down, and these droplets are forming in front of the walls. So inspired by this, recently with Daniel and Mark, and also our research system tested vehicle, we've been looking at this in spherically symmetric geometry. So we've taken, rather than looking at bubble walls expanding, we've taken a spherical droplet and let it shrink in on itself. And we actually can get, again, this is just like a ideal fluid, and there's no extra physics inside the droplet, because it's just hydrodynamics and equation state. So we end up with a self-similar droplet forming here. And we can see actually, even with this kind of idealized geometry, we can see the same wall velocity slowdown. Note here that the velocities are minus because it's inward into the center of the droplet. But you can see qualitatively the same. So, for example, the slowest case here, 0.34, is the same. Not second slowest, 0.34 is the line green again. This is what we had, and what we had is the slowest case in the previous page. Has it basically almost goes to zero wall velocity, whereas the indigo one, the 0.005, which is even a bit weaker than the one we had before. Basically, the walls don't slow down at all; they just collide into the origin. So we can do self-similar droplets here, and we can therefore separate the physics of these droplets out and look at it more carefully. And we're currently working on trying to understand how these suppress the gravitational wave signal. And this is a plot from our earlier paper on these strong transitions with Mark and Daniel. And here, this is a plot of wall velocity on the x-axis against the peak fluid velocity on the y-axis. And basically, we did a scan of points. The middle colored circles are the points where we simulated the system here. And the redder the points are, the lower the gravitational wave signal is than expected. And this is mostly, we think, due to the formation of these droplets and the consequences it has basically for the energy budget of these scenarios. And it's therefore they're available kind of kinetic energy and the right degrees of freedom to source gravitational waves. So, for example, this case here I was just showing you is this bright red points. The movie and also the lime green curves on the past two pages are this bright red point at the left for the 0.224 column of points there. And this is based on our earlier work. We think that this represents potentially as much as a 1,000th, a factor of 1,000 suppression of the gravitational wave signal in this scenario. So that's why if your hopes are resting on gravitational wave signal being detected here, then that's quite alarming. So we want to make sure we understand that properly, which is why droplets are now an interesting thing to look at. So just before I finish, I want to thank people I work with, so the students and research assistants that I work with, my former and current postdocs, Daniel Cutting and Oliver Gould, and my collaborators, which for the work I've talked about today include Jonathan Kozaczuk, Mark Heinmarsh, Stefan Huber, Hiran Patel, Michael Ransom-Rusov, Kai Romokan, and Thomas Denkerman. So what do I want you to remember? If you remember two things, I want to do with dimensional reduction, I want to do with droplets. I want you to remember that dimensional reduction is a valuable thermal field theory tool, and it lets us test perturbative studies of phase transitions. I want to also inform you that in these strong phase transitions, when alpha gets large, these hot droplets can slow the completion of the transition and may suppress gravitational wave production by quite some margin. Exactly how and why, we're still investigating. And some questions that you could ask me now includes why haven't I talked about bubble nucleation calculations? You could ask me, but you could also ask Chiara or Alberto about the onsets of shocks and turbulence. And you could also ask me about the physics, other physics that could explain this gravitational wave suppression. But with that, I'll thank you for your time and hand back to Marika.
Yeah, thank you for the nice overview. Are there any questions? You can either raise your digital hand or just speak up or write them in the chat. I see a question from Mark, please.
Well, maybe it's more of a comment concerning the droplets. Because essentially, well, one could argue that it's not obvious how to calculate wall velocity in a given model. But to be honest, from the results I know, it's very difficult to get a strong transition with slow walls, which is essentially, because I understand that for your simulation, that's basically an input, right? So if we, well, doing a calculation, you always do in electric baryogenesis. When you get alpha to be 0.1, the velocity is typically already 0.7 or something. So it's really, the walls get fast really quickly. And then essentially it seems that the speed just jumps to 1. Because when there is no, right, that was the point of Jim Klein's recent paper to some extent, that as soon as there is no plasma shell in front of the wall, so when you switch to detonations, essentially you can find a solution, at least using the fluid ansatz with velocity smaller than 1.
Thank you for the comments. I don't think that, I think that's an important point, but I don't think it necessarily undermines the interest of looking at these droplets. For example, one could think in strongly coupled field theories, albeit the equation states a little difference there, they do play a role. They were originally studied in this context from the point of view of potentially first order QCD phase transition in the early 1990s. So I think droplets themselves and there's plenty of phase transition scenarios in which the behavior of the wall is such that you don't necessarily end up with a very fast wall velocity. I think it's you're correct in your point in pointing out that yes, this might need some fine tuning, but I would argue there's plenty of other things that we talk about need fine tuning too, and that's never stopped me in the past. So, but thank you for the comment.
Oh, well, I wasn't trying to say that you shouldn't look into them. It is very interesting. But what I am trying to say that it's not obvious if you really have to worry that much about this suppression in a simple BSM model. I'm
not worried. I'm looking for pretty pictures mostly.
Maybe I can ask a follow-up on that, because can you go back to the slide with the red dot? Where the droplets were important. To one, yeah, this one. So it looked like a very isolated point, right? Or at least region. So what is special about these parameters? Because how do you translate them to model parameters?
That's a good question. So yeah, this requires strong transition, so that large alpha, yes, but also you would need to tune your wall velocity to be, as Marcus pointed out, quite small. But also, I would also point out that's a worst case scenario. You can also see here that anything which is a strong, somehow ends up being a strong deflagration here, also has some suppression by as much as an order of magnitude. So you can see that like this 0.57 or so point with the green one just left of the vertical dashed green line. We didn't study hybrids in this case, but there's already some suppression there. Whereas for detonations, it's pretty much unharmed. So yeah, the exact how you exact map this to your model specific parameter would depend on how you understand the wall velocity for a particular model, which is why we depend on people like Jessica and other speakers today improving their predictions, and then maybe we don't have to worry about droplets anymore. But like I said, I'm mostly in it for the pictures.
Thanks. I don't see any further questions, so let's thank David again and maybe continue with our next talk. So our next talk is by Marek Levitt, and he will talk about gravitational wave from bubble collisions in the first order phase transition. So please go ahead.
Oh, thank you for the introduction. Yes, so thanks to David's review, I won't have to, luckily, well, explain any of the basics. So I'm very grateful for that. Essentially, I will be talking about, let's say, a complementary case in which the fluid dynamics don't really play a role. So the whole talk is based on this series of papers. The first part concerning the energy budget is in those 3 papers, and then there is, we'll see a derivation of the bubble wall collision signal, which was presented in those latter 3 papers. Okay, so starting with let's say motivation. Of course, as you all know, well, gravitational wave physics have a very bright future ahead of them, essentially because, well, right now we only have several experiments active. There are several pulsar timing arrays, and there is LIGO, Virgo, Kagra, which are operating right now. But in 10 years or so, we expect to have this broad overview of the spectrum, which looks very nice. So of course, further improvements in pulsar timing, 3rd generation terrestrial laser interferometers. Then there will be finally space interferometers. And what I should point out also, there are various experiments aiming at the mid-frequency between LISA and ET. One of them is ION, which aims to probe this with well, cold atom interferometry techniques. But essentially the plan is to have ion kilometer running roughly by the same time as LISA and ET. And perhaps in the future, the space-borne version of the same experiment called EDGE will also be realized. Okay, but with those very optimistic prospects, there's nothing else to do than just well, try to assess what part of model parameter space we will actually be able to probe using all of those. And to do that, well, we go back to the basic parameters. So those were explained many times over throughout the last 2 sessions. So first, strength of the transition. So just energy of the scalar over the radiation density. And then, well, HR, which is normalized size of the bubble. But this, again, just corresponds to 1 over beta over h, essentially. And beta over h is typically more convenient because that's something you can calculate from the action directly in a given model. Okay, but that was, as was also mentioned in the talks before, essentially there are a few, let's say, main possible sources of gravitational waves that people have looked into. And well, the oldest one actually is collisions of bubble walls, but then, let's say, more of the emphasis was put on plasma effects of sound waves and turbulence. I will actually try to talk mostly about the first one. And to start, yes, so, well, the big question that we have to answer to see if it's even possible to have any bubble collision signal in a given model is to see where the energy goes in a transition. I'm sorry that my plots are not maybe as nice as David's, but you can tell no information was actually derived from them. They are a secondary effect. I just put them together to try and explain this. But essentially, the point is that bubbles, as they nucleate, are absolutely tiny compared to their size at collisions. Typically, those are 10 orders of magnitude or more of growth. So again, those should be much smaller, but then you wouldn't be able to see anything. But essentially, then the bubbles grow, and the question is, so in most of the talks that we've seen up to now, what will happen is that the acceleration will stop due to friction from the plasma. But the question is it possible that the bubble actually keeps on accelerating all the way up until the collisions happen? So to answer this question, what we need is well, computation of how much energy actually goes into the wall. So the simplest way to write down the energy of a thin wall bubble, so just a shell at radius r, very simple model, is to write down surface density and the energy stored in the volume. The surface density, as you see, grows with gamma of the wall, while the volume factor is essentially, well, if we had only the scalar, it would just be the energy that we gain converting to the lower energy vacuum. This would be, P would just be equal to P0. But of course then, well, there were developments over the years. Firstly, there is this one-to-one process, so leading order correction, which as you see was constant. So actually for a while, it seemed that this acceleration will not stop provided that the strength of the, well, that this is a positive number, because essentially this is a constant. However, later on, and Jessica already explained this much better in the previous session, and we will actually use her result, not the Boddicker and Moore one, in what follows. But essentially, the next to leading order corrections with resummation give you a correction which goes as gamma squared. Maybe the growth with gamma squared isn't crucial because we checked that, well, switching between the two models actually doesn't change the parameter space as much as you would think just looking at the power of this, of the expression. But still, the result is different. And so you see that basically the difference comes from the fact that this will always have a zero at some finite gamma. So essentially, we will always have a gamma at which the wall ceases to accelerate, and this is very easy to compute. Another gamma factor that is of importance to us is the size that the walls would reach by the time they collide if they hadn't stopped accelerating. Well, given by a much simpler expression here. And essentially, to calculate the total energy budget, we just compute the integral of this. This is very simple. Basically, as long as the wall keeps accelerating, the energy goes into, yes, as long as the wall is accelerating, the energy goes into the wall, which becomes more and more energetic. Yes, so basically, as long as gamma star is smaller than gamma equilibrium, which means that the walls did not stop accelerating by the time they have collided, we get something which is basically equal to 1. So this is, yes, this number will be very small. This might be a fraction, but also close to 1. And essentially, the efficiency can be large. In any other case, where the walls have stopped, by the time they've collided, essentially, it goes down linearly with gamma. And then, of course, if we want to also compute the sound wave contribution, we need to just take out the energy that we use to accelerate the walls from the total using this alpha effective. But let me show you a very simple result. This is from my U1B minus L model, which is a classically conformal extension of DSM, where we have one new scalar with this U1B minus L symmetry. But the reason I'm showing you this is a very simple model. It has just two parameters, G, so the gauge coupling, and the mass, which essentially sets the scale of the transition. And if we look at this plot, this is the strength of the transition. As you see, when we decrease G, alpha increases, so we increase the supercooling. Well, and the interesting part where we switch to collisions being the dominant source is a discontinuous line, which, as you see from this plot, corresponds to alpha being 10 to the 12 or something. So we're not, well, when I'm saying strong transitions, I don't mean alpha equal to 1 or 10. It's really many, many orders of magnitude. So there was a significant period of inflation before the collisions finally happened. And this is basically what this plot is showing. So kappa collisions is large below the red line, and kappa sound waves dominates above the black line. Okay, but we'll get back to this in a second. So essentially, to try and see what is possible in various types of models, we tried to do as generic study as possible. So we just used a very simple potential in which I can really probe the entire parameter space because there is a very simple semi-analytical solution, but one can check that this is actually quite accurate. And as an example, in a very simple high temperature expansion. So there's no barrier at t equal to 0. But essentially, we can probe the entire parameter space. So these are points that various gravitational wave experiments will actually see in terms of alpha and beta over h. But what this plot tells you, so essentially, this region is cut from above by the sensitivity of experiments, but it's cut from below by us just not populating that area at all. And the message here is that it's essentially very difficult to supercool. So it's very difficult to lower beta over h or increase alpha beyond a certain limit. And essentially, well, there's no zero temperature barrier in this case. But if we introduced a barrier at 0 temperature, we would see a similar thing. The only problem is that then you can fine tune and it becomes much more difficult to tell whether the picture you're looking at is actually allowed, and one needs to look at percolation much more rigorously. But we have tried that, and indeed, we never really find points with large alpha or small beta over h in the parameter space of polynomial potential models. So instead, as was also already mentioned, generically, one needs to look at classically scale invariant models. So essentially potentials that look like this. As you see, this is not a polynomial. We have 5 to the 4th and a logarithmic correction. And then, as it turns out, there are no problems with percolation. Essentially, just lowering this value of g, we can produce as strong of a transition as we want. This actually continues. We just cut it at 10 to the 10. But there's virtually no problem. So this is the type of models that can really support these solutions. Okay, so now knowing this, we can try and calculate the spectra. So back in the good old days, the most typical method was to try and use the envelope approximation, which essentially means, so these are two bubbles. As I'm sure you can tell, this is the energy density. These are two bubbles that have collided. And as you see, so in the envelope approximation, essentially what you do is all the collided part of the wall is actually gone. And of course, the energy outside is just the vacuum energy that the wall acquires as it grows. Maybe you can't see this very well because the wall is very thin, but there is a lot of energy stored on the surface area. But in practice, if you do the simulation, of course, the energy doesn't just disappear. You can have many interesting results from this. Now, so it's actually not a completely trivial question what happens with this energy. There are basically, well, there's at least one effect that's been identified to make a big difference, and this is so-called vacuum trapping. So you can see, well, what we're looking at here is the energy along the collision axis. So this is actually two bubbles initially, and then as the time grows, you see they collide somewhere here, and the outer wall just keeps expanding. But there's this strange effect that, as you see, well, this is just the energy, so you can't tell. But essentially, the field at the point of collision is pushed back to the false vacuum, which means that what you have here is a false vacuum bubble. This is why it eventually starts shrinking, it doesn't grow anymore. Well, because it energetically has to disappear eventually. So then you will see this effect. And as you see, the energy will then be stored mostly at the point of collision. But instead, if you don't have trapping, and that depends on the potential, essentially, if you have similar minima with a large barrier between them, you will see trapping. But if this doesn't happen, as you see, essentially you lose some energy, but most of it just travels where the wall would have been in form of gradients propagating onwards. And essentially, very broadly speaking, it's easy to have trapping in polynomial potentials, but in scale invariant models where you really expect this signal to be significant, it doesn't happen at all. One can actually check this analytically. There's a very nice paper by Ryusuke and Thomas Konstantin from some 2 years ago. And indeed, no trapping really occurs in potentials where you would expect this signal to be significant. So what do we learn from this? Essentially that we...
Sorry,
yes?
you have 5 minutes left.
Okay, that's perfect. So the method to compute the signal is actually the same as with the envelope approximation. because still, what you had to do, even using the envelope approximation, was to do an approximate 3D simulation. Essentially, you nucleate bubbles, but you don't have to keep track of the field at all. You just assume that the bubbles are spheres with a certain energy density, and then when they collide, the energy goes away. So that was the envelope approximation. But then that was improved several years ago. So there were papers by Gino again and Konstantin. This is actually, the plot is from this paper. The improvement was a bulk flow model where the energy goes as R2 minus 2, which you would expect just based on the energy conservation in the shell, which, as you see, quite trivially means you don't drop the collided part of the wall, but the energy starts going down after the collision with the radius. So what we did together with Ville was basically the same thing. The only thing we really improved was to try and track the scaling of the energy based on simple lattice simulations. So as long as you do a more symmetric lattice simulation, so we assume cylindrical symmetry here, it's very easy to have quite energetic walls and still well, be able to extract the scaling. So this is again in, well, essentially a U1 B minus L model. But there are a few parameters. So firstly, there is G, which is a scaled gauge coupling. This is quite important. But secondly, you see there is a phase difference, because essentially we're breaking a U1 symmetry. So there is not only the value of the field, but also the phase. And indeed, different bubbles will be nucleated with different phases. So this does matter. And in the example here, what we have is, so this ignores gauge bosons. G was set to 0 here. But there was a phase difference of pi over 2. And what you see is the propagation of the energy after the collision. And again, we can, well, just track this more easily, just plotting the energy on that line. So that would be the blue line here. And the power law here is R2 minus 2. And this is indeed what you would expect, as it turns out, from global symmetry breaking. Global because G was set to 0, there are no gauge bosons. But interestingly, when you turn on gauge bosons, maybe setting G equal to 10 looks strange, but as I said, it's a scaled coupling. And essentially we checked using realistic potentials that this is the value of this scaled coupling that you would see in very energetic collisions. And then this behavior changes. Essentially, as you see, it starts following R2 power minus 3 instead. So the energy is dissipating faster because you are producing gauge bosons. And this is actually something you would also see if you just completely forgot that you had a U1 potential and just did a 1D simulation with a scalar. You would also see this R2 power minus 3 evolution. Okay, so knowing this, we just do the calculation again, nucleate bubbles randomly, and just have them scale by what we know from those lattice simulations, and these are the results. Essentially, this is a fit to the spectrum. There are all the parameters, but there are two main points here. Firstly, as you see, the envelope, it mostly fails at high frequencies. And this is simply because, well, cutting out all of this propagating energy, you also introduce very sharp features as sources, which seems to be the source behind all of the, well, this very slow decay. With this gone, as you see, all the power laws essentially look quite similar at high frequencies and much more steep than in the envelope approximation. In fact, the power is, well, approximately 3. This is the high frequency power. But there is an interesting difference in the low frequency part of the spectrum, which essentially corresponds to larger scales. So when the energy dissipates slowly, R2 minus 2, as in a global symmetry breaking, you would see the power, well, omega goes as F2 power 1, which is also the result of the bulk flow model. But then when you introduce gauge bosons, it starts going down more steeply. So, well, 2.25 roughly. And then if you increase the power such that the energy is disappearing, well, quicker and quicker, you go closer to the envelope, but still at high frequencies, it seems you would need to introduce really sharp decay in order to go back to this f2 power minus 1, which the envelope predicts. Okay, and this is actually all that I have for you. So just let me recap. So first, to observe bubble collision gravitational wave spectrum, we always need very large fine-tuning, so alpha 10 to the 10 or something of this order. But this is in a sense a positive information because of this we know how the potential looks like. If we see a bubble collision spectrum, we will know it essentially came from a scaling invariant potential. So this is one thing, and the other is that the shape of the spectrum can actually encode a whole lot more details on the particle model. It seems that well, the low frequency power actually encodes whether we had a global or a gauge symmetry breaking just by the power of the low frequency slope. And yeah, that's all. Thank you for your attention.
Thanks a lot for the interesting talk. Anyone has a question or comment?
Yeah.
I see David.
Yeah, so thank you, Eric, for a really lovely talk. It's always fun hearing about these things. I think I have one kind of question, which is how do we actually go from studying these things in 2D to making quantitative predictions about the actual 3D universe that we live in? Because pairwise bubble collisions often have systematically steeper power laws at the high frequency end than in 3D. And I think your own papers have shown that several times, comparing it like to the work that we have, but also just going back all the way to kind of like the earlier, kind of even just the envelope approximation. If you pair collide a couple of bubbles together and impose a cutoff, you'll get a steeper power law than you do if you have the envelope approximation for many bubbles. So do you have any ideas on how we can go from making quantitative predictions based on pairs of bubbles colliding to the real universe of 3 dimensions with lots of bubbles?
Well, yeah, well, the calculation we did is that essential, right? So well, this is a simplified lattice simulation, but then in the end, we put that in a 3D box and then nucleate bubbles and track the energy going down after collision just as a function of R. So this is an attempt in that direction. Does that answer your question?
So do you, yeah, so I'm not, yeah, I think I need to think about that a bit more before I say for sure. It doesn't look like it changes the power laws very much, does it? Like in this like B doesn't change very much. I guess that's the low frequency power law. But
B is the high frequency power law.
Okay, so I did that. Oh wow. Okay, so it doesn't change much at all. Interesting.
Yes, they look all the same and numbers.
Yes, that's interesting because like systematically you expect it to change quite a lot as you go to 3 dimensions. So I think my question still stands, but maybe we can talk about it offline.
Yeah, we will have the discussion session afterwards.
Are there any other questions? Seems like your talk was very clear, and if some questions come up, we'll have the discussion session as you mentioned. So maybe for now, let's continue with the next talk. Let's see.
Does that work?
Yeah, looks good. Can you go forward?
Okay.
Yeah, so the next talk is by Jorinde van der Vis, and she talk about the model-independent energy budget of gravitational waves from first-order phase transition. Please.
Thank you, Marike. And thanks to the organizers for organizing this very interesting workshop. So I'm going to talk about one computational aspect of the prediction of the gravitational wave signal. This is work that I did in collaboration with Felix Giese, Thomas Constantin, and Guy Schmitz. And let me get started. Okay, so as almost all of the talks today, I'm talking about first order phase transition, which could be the electric phase transition or another kind of first order phase transition, doesn't matter, which gives rise to the formation and the collision of bubbles. And in this process, gravitational waves are formed. I think it's very nice because in the talks of this afternoon, we've actually heard about contributions of 3 different kinds. And in this talk, I'm focusing on the contributions from the plasma, so the sound waves. Now, imagine that you are a model builder. So you have come up with some model which gives you first order phase transition, and then you want to predict the gravitational wave signal. Then in principle, you would have to run numerical simulations, but these are very computationally expensive. So fortunately, they have been done by a couple of people that are also in the audience. And it turns out that the signal coming from these simulations can be described by a fit. And this expression here gives the amplitude of this of the predicted gravitational wave signal. And then there's also a shape which is universal. Now let me go through the various quantities appearing in this formula. So F is the redshift, H star is the Hubble parameter at the moment of percolation, and R star is the mean bubble separation. And all of these quantities depend on your particle physics model at finite temperature and the bubble wall velocity. Then there is omega tilde, which is extracted from the lattice. And in the prefactor, there is the time of shock formation. And this can be roughly approximated by K divided by gamma, where gamma is the adiabatic index, and it depends on your equation of state. So what is left now is K, the kinetic energy fraction, and that's the topic of this talk. So what is K? It's the ratio of the kinetic energy in the plasma divided by the energy density that was available at the onset of the phase transition, so at the nucleation temperature. And you can determine this quantity actually by solving the hydrodynamic equations of a single expanding bubble. So this is much simpler than solving the hydrodynamic equations for all of these bubbles. This thing depends on the phase transition strength, and as we will see, it also depends on the speed of sound of the plasma. And in addition, it depends on the bubble wall velocity, which is not easy to compute, as we've seen, but that will be treated as an external parameter in this talk. So the goal that we had in our works was to determine this kinetic energy fraction as a function of the phase transition strength, the bubble wall velocity, and the speed of sound without any further model dependence. And the reason that we wanted to do this is to provide some methods which can be used by other people that are maybe more interested in model building, such that they don't have to solve the hydrodynamic equations. Okay, in order to understand how we can do that, let us first have a look at the hydrodynamic equations of a single bubble. So the plasma in this case is described by perfect fluid. So this depends on the enthalpy, the fluid velocity, and the pressure, where the enthalpy is just the sum of the pressure and the energy density. Then the hydrodynamic equations follow just from the continuity equations. I will show them in a second. And if you integrate these continuity equations from right behind the bubble wall to right beyond the bubble wall, you get a set of matching equations that are written here. So in this slide and also in the rest of the talk, a plus denotes a quantity right in front of the bubble wall, and a minus is something right behind the bubble wall. So these are the velocities of the plasma right in front and right behind the bubble wall. And these matching equations depend on the pressure and on the energy density. So they depend on the equation of state. Now, if you solve these hydrodynamic equations, you can get 3 types of solutions, as we have also seen before. So there's a detonation solution in which the wall velocity is supersonic. In this case, there's a rarefaction wave behind the bubble wall, and the plasma is at rest in front of the bubble. Then there are deflagrations in which the bubble wall velocity is slower than the speed of sound. In this case, the plasma is at rest inside of the bubble, but there's a shock wave in front of the bubble wall. And then there's the hybrid case, which has both a rarefaction wave and a shock wave. So this is an example of a velocity spectrum. So it turns out that these solutions are self-similar, meaning that they just depend on this coordinate c, which is the distance from the center of the bubble divided by the time since nucleation. So in this case, the wall velocity is 0.7. And you see that the fluid velocity is both non-zero in this rarefaction wave and also in the shock wave. On the right-hand side, I show the enthalpy and the entropy. And you see also that they are varying both inside of the shock wave and in the rarefaction wave. And then if you go beyond the shock wave, then you're actually back at the same enthalpy that you had at the nucleation temperature. Okay, so these equations were solved for the Back equation of state. So the Back equation of state is a simplified equation of state, which is given by a radiation-like contribution in both the symmetric phase, which is denoted by S, and the broken phase, which is denoted by broken. And then there is a Back constant, epsilon, which parameterizes the vacuum energy difference between those two phases. And this epsilon is independent of the temperature. But this is really a simplified situation. And in a situation, the speed of sound is always 1/√3. Now, in this specific model, you can define a phase transition strength that is based on this Back constant. Now, in this 2010 paper, the hydrodynamic equations were solved for this model. So they computed the velocity profile, and by integrating over that, you can get the kinetic energy density. And as a result, this quantity kappa, the efficiency factor, could be computed. And this kappa is just a function of the bubble wall velocity, v, and the phase transition strength. Now, the kinetic energy fraction, which enters in the formula for the gravitational wave spectrum, can easily be obtained from this efficiency factor here. Now, in this paper, the authors provided a fit. So they gave this kappa in terms of alpha, the phase transition strength, and the bubble wall velocity. So this result has actually been used really a lot in the literature, because other people just took, if they had a different model for their first order phase transition, what they did was just map their model onto this Back equation of state and then compute the kinetic energy fraction from the efficiency factor that came out. So in order to do that, they had to compute some phase transition strength in their model, but there's typically no Back constant in their model. So it's not completely clear how you should compute the phase transition strength in a different model. And moreover, a different model will likely not have a sound speed that is exactly 1/√3. And there's no room in the Back equation of state to account for that. So,
Jorin, I think it's about 5 minutes. That's correct?
Just 5 minutes?
So did I miss it? I think you started around 20 past, right? Or was it? Am I missing? Maybe I was confused. Sorry. Did anyone check? Sorry.
I think it was more 25 past, but I was also not paying that much attention.
Sorry, I forgot to check actually.
I think I've not been talking for 50
maybe I missed
minutes.
5 minutes. So this is
okay.
a warning. Sorry.
Okay. So, okay, how is this generalization to other models done in the literature? Bear in mind that if you're not solving the hydrodynamic equations yourself, what you know typically is just the nucleation temperature. So you do not know the temperature in the plasma. So any phase transition strength has to be evaluated at the nucleation temperature. There are typically 3 ways in which this is done. So here I'm defining some notation. So this D denotes that the quantity is evaluated in the symmetric phase and then in the broken phase, and the difference is taken. So these 3 definitions appearing in the literature are based on the pressure difference between the 2 phases, the energy density difference, and the 3rd definition is based on the difference in the trace of the energy momentum sensor. Now, note that these 2, if you would compute this for the back equation of state, you wouldn't even get back alpha epsilon. That is the phase transition strength in the back equation of state. So this is already suspicious. This is not the case for the one based on the trace. But what all 3 approaches have in common is that the speed of sound never enters, whereas it's typically not 1 over square root 3 in different models. So let's see where the model dependence of your model actually enters in the hydrodynamic equations. So these are the hydrodynamic equations that you get from your continuity equation. So they're for the fluid velocity V in terms of the coordinate xi, and for the enthalpy. Gamma is just the Lorentz factor, and mu is the boosted velocity. So really the only place where that has some model dependence is in the sound speed, which enters here and here. But in addition, there's also model dependence in the boundary condition. So in the matching, and also in your boundary condition at large xi for the enthalpy. Now, in order to reduce this model dependence, we made an approximation. So first of all, we assume that the speed of sound only varies very slowly in either phase, so that we can describe the speed of sound in the symmetric phase and in the broken phase by a constant. And in addition, we assume that the temperature is also, so the temperature in front of the wall and behind the wall are roughly the same. And after making this approximation, the matching equations actually only depend on the speed of sound in the broken phase and some newly defined phase transition strength. And this phase transition strength is very similar to the one based on the trace of the energy momentum sensor, but we have defined something that we call the pseudo trace, in which this is not a factor of 3, but the sound speed squared. And this matching equation can easily be solved for B plus or B minus, because typically the other one is known. Okay, so what we've done is we've captured the model dependence of the hydrodynamic equations and the matching in just a small number of parameters. The phase transition strength, the speed of sound in the broken and the symmetric phase, and in the bubble wall velocity. And then we can determine this efficiency factor, which is slightly different than the one in the back equation of state, but it depends on the fluid, the kinetic energy in the fluid, alpha, and the enthalpy. We can now determine this in a model independent way, and then it's very easy to compute the kinetic energy fraction K from that. But then you have to multiply it by a factor which does depend on your model. There's a tricky detail. So to make this user friendly, you have to define this alpha theta bar in terms of the temperature at nucleation. But this is not T plus, which is the temperature that enters in your matching. So in order to relate this Tn and your matching for hydrates and deflagration, you have to do a shooting algorithm. Okay, so quick recap. We wanted to find a model independent expression or computational method to find the kinetic energy fraction. And we introduced something that we called the pseudo-trace and a phase transition strength based on this pseudo-trace. We then found that the velocity profile, but also this efficiency factor, can be determined in a way that only depends on these quantities. And then it's very easy to obtain the kinetic energy fraction from that. Okay, so that was part one of the goal. The second part was to make this result reusable for other people such that they don't have to solve the hydrodynamic equation. In order to do that, we proposed to, instead of mapping the model onto the back equation of state, to map it onto what we call the template model, which is a model with a speed of sound that can deviate from 1/√3, but is constant. So it's sort of a generalization of the back equation of state. And we have a quantity nu and mu appearing here, which depend on the speed of sound. We then provided a Python snippet, which computes the efficiency factor in this template model. So all you have to do is compute the phase transition strength in your model, the speed of sound, and choose some wall velocity, or compute it, of course. And then this piece of code spits out the efficiency factor, which you then have to multiply by this quantity to get the kinetic energy fraction. And that goes into the gravitational wave spectrum. Okay, now let's have a look whether this works or not. So what we did was a comparison of the full hydrodynamic equations with our new approach, which is based on mapping onto the template model, and these four approaches that are known in the literature. So these are both based on the difference in the trace of the energy momentum tensor. This is the pressure difference, and this is the energy density difference. And we did this for two toy models. One is standard model-like. So you could get a first order phase transition in the standard model if the Higgs would be much lighter, and then you would get a free energy, which is related to the pressure that looks like this. So there's a phi to the third term. And the other toy model is a two-step phase transition, which you can get, for example, if you couple the Higgs to an additional singlet, which first gets a VEF, and then in the second step, the Higgs gets a VEF. So here I show the parameters of these models, and this is showing the sound speed in the broken phase, and these are the phase transition strengths. So these are all relatively weak phase transitions. Okay, then this figure shows the comparisons of methods 2 to 6 relative to method 1, which was the full hydrodynamic solution without making any additional assumptions about constant sound speeds or whatsoever. So when something is right on this line, it means it matches the full result, and the further it is away, the more it deviates. So first of all, method 2, which is our proposed method, can be seen to lie very close to the full solution. Only in the case of detonations and hybrids and, well, relatively strong phase transitions, we see some deviations, but these are, so typically they're sub% level, and here they're a few percent. Then method 3 and 4 are based on the difference in the trace of the energy momentum tensor. They typically show a somewhat larger deviation from the mapping onto the template model. And then the computation based on the difference in the energy density and the pressure density shows very large deviations from the full numerical result. So can deviate more than 100% in either direction. So this shows that particularly the energy density and the pressure density are not good quantities to estimate the phase transition strength. Okay, that brings me to my summary. So we've shown that you can use our newly defined phase transition strength based on the pseudo-trace. the speed of sound in the broken and symmetric phase, and the bubble wall velocity as a model-independent parameterization of the hydrodynamics. You can then compute the efficiency factor in a model-independent way, and it's very straightforward to compute the kinetic energy fraction from that. The previous graph showed that if you take the Bag equation of states and you just plug in phase transition strength based on the pressure and the energy density, you get a very bad estimate of the kinetic energy fraction. Whereas matching onto the template model, which is the method that we proposed, gives the most accurate approximation of the kinetic energy fraction and therefore of your gravitational wave. Thank you very much.
Thank you for this very clear talk, and sorry for my premature interruption. Are there any questions?
I have a question. Can I? So thanks for this very nice talk. I have a question regarding very strong transitions, because as far as I understand from your summary plot comparing different methods, basically all of them work worse for very strong transitions, right? Doesn't mean that they work bad, but as you...
But strong in this case means still smaller than...
Yeah, that's not strong that I would mean, but okay. But then, is there a good method for really strong transitions with alpha above 1, let's say?
Well, I think so. What you could always do, of course, is solve the whole thing. Just solve the hydrodynamic equations numerically yourself. But I think what you have to worry more about is that the fit that you use which came from the numerical simulations, is probably not working very well anymore in that case. So I'm not sure how relevant then computing the energy budget very carefully is anymore, because you're plugging it into a formula that is no longer valid.
Okay, I see. Because I remember in I think the expression coming from the back model, the dependence on alpha drops out basically for large alpha. I mean, really large alpha.
Yeah, but you mean the lines become closer and closer to each other?
No, there is this formula with like alpha over 1 plus alpha, something like that, right? And then if alpha gets really large, then, well.
This here.
Yeah, exactly.
Yeah, but this kappa still depends on alpha.
Okay, yeah, I don't remember the details now, but somehow it seemed to me, okay, it's not relevant here. Anyway, yeah, okay, you answered my question. Thanks.
Okay.
Are there any other questions? How much work is it actually to do the full hydrodynamical calculation? Because you could also provide a snippet for that, right? And do no matching at all, or is that not?
Yeah, but then what you would have to provide as an input is the potential, I guess. Yeah, I don't know. It took us like more than a few days to figure out how to do it. It's yeah, sure. You could make a piece of code for that.
But would that be much more complicated or take more time if you? I don't know. So, well, what is the advantage that you just don't have to run the code at all, but you can just match it to them? If you use your results, say I have a model and I wanna.
Well, I think it's much easier if you just if you just have your model, you've computed your phase transition temperature, etc., and your sound speed, and you plug it into this code snippet that I would say saves you well, it depends on how smart you are, but maybe a week of coding, or it depends on how familiar you are with it, of course. But
Okay, thanks. Are there any other questions? I don't see a raised hand anymore, so thank you for your talk. And let's continue with the last talk of this session.
Hi, hello, can you hear me now?
Yes.
Okay, and can you see my screen?
Not yet.
Oh, sorry. What about now?
Yeah, now it works. Thanks. So yeah, as I said, the last talk of well, for me this afternoon is by Alberto Ropopo. So please go ahead.
Okay, thank you very much. Yeah, in first place, thank you very much for the organizers for inviting me to give this talk and to give the chance to present my work. Thank you also to the speakers before me, because they have already explained a lot of the information. So in cosmological phase transitions, so I won't need to go into much detail in the introduction, which will allow me to go into the final results. So I will be presenting the work that I have done in the last few years with these collaborators. But previously, I think they have been called the Nordita group. So so I will be presenting results on these papers, and if I have time, I hope I'll have some time to present some results of this latest paper that was just yesterday posted on the archive. So yeah, this is just a quick overview. So let me start with a very quick introduction that has already been explained. So we expect generation of cosmological gravitational waves during different phase transitions that we have in the early universe. And as Chiara was explaining, if we consider the frequency bound by LISA, then we can see that then a signal coming from the electroweak phase transition is expected to peak around the peak sensitivity of LISA. And also similarly, if we have signals coming from the QCD phase transition, we expect that to peak around the nanohertz range, which are accessible by pulsar timing array. So we can probe the signals coming from these phase transitions with space-based detectors as well as pulsar timing arrays. This is just an overview of these. Like we have the ground-based gravitational wave detectors in the largest frequencies, and then we have the space-based detectors as LISA, and second generation space-based detectors as Big Bang Observatory or the SIGO. And this is such a signal coming from turbulence generated gravitational waves from the electroweak phase transition. And in the lowest range of nanohertz, we can also have signals coming from QCD that could also be detectable. And then if we go to even smaller frequencies, we have the anisotropies of the polarization, of the CMB polarization. So what I'm going to be specifically talking about is on magnetohydrodynamic sources of gravitational waves. The sources coming from hydrodynamic turbulence produced due to first order phase transitions have already been discussed by Chiara, by David Weir, by Marek Levitt, and by others. And I will be talking a little bit about it, but mostly I will be focusing on the generation of magnetohydrodynamic turbulence due to the presence or generation of primordial magnetic fields and the subsequent generation of gravitational waves. So other sources of gravitational waves, they have already been discussed. So I'm going to go over it. And what we are doing, we're conducting direct numerical simulations. We are using the Pencil code, which is an open source code given here and stored in GitHub, which solves in general magnetohydrodynamic equations, in which we coded the gravitational wave solver in order to couple the generation and the evolution of magnetohydrodynamics, and to couple that with the generation of gravitational waves. So we will be solving the relativistic MHD equations adapted for the radiation-dominated era, and therefore subsequently computing the generation of a stochastic background of gravitational waves. So let me go quickly through. I'm going to go very quickly through some details on the primordial magnetic fields, but I will focus on talking about the production or presence of magnetic fields during cosmological phase transitions. They are strongly coupled to the primordial plasma, and therefore we expect them to generate magnetohydrodynamic turbulence, as has already been explained in previous talks. And on the other hand, even if they are not generated during the phase transition, we can also expect if there is a present magnetic field that has been generated at earlier epochs than the phase transition, then that would be reinforced by the primordial turbulence. Or also we can expect if there is a hydrodynamic turbulence that magnetic fields can also be generated due to via dynamo, due to the hydrodynamic turbulences we studied in this paper from 2019. So why do we expect to have primordial magnetic fields? So on one hand, there are many astrophysical evidence of very large scale coherent magnetic fields, but in particular, very interesting for this application, for this specific idea is that the observations by Fermi telescope, where they were observing power removal coming from gamma ray beams. And therefore this could be explained if we consider that we have magnetic fields, which is coherent in very large scales up to the scales in the cosmic void. So they could be filling the whole universe. And this is very difficult to explain from astrophysical sources. So one usually expects this to be generated during cosmological epochs. So we expect to have some cosmological seed fields that are subsequently amplified during the structure formation and up to the present time. So this is another way to probe these magnetic fields, which would be parallel to the potential detection of gravitational wave signals that are coming from these magnetic fields. Two ways of detecting such primordial magnetic fields. An important aspect of these magnetic fields is helicity. So this is a plot where we started from a magnetic field generated at the electroweak phase transition with a maximum amplitude. In the y-axis is the amplitude of the magnetic fields, and how it evolves with respect to the coherence length scale depends on the helicity. So I'm not going to go into much detail about this, but the idea of this plot is that we require a fully helical or at least partially helical magnetic field initially, in order to hold for the lower bonds that are imposed by these observations of base spectra, if we are also limited by the maximum energy density that can go into magnetic fields, which is also given by an upper bond given by the Big Bang nucleosynthesis. So therefore, we expect primordial magnetic fields. We expect them to be helical. One way to obtain these magnetic fields, for example, would be due to the velocity fields that are induced by first-order phase transitions that have already been discussed in many detail. And therefore, these since they would be strongly coupled to the magnetic fields, there could be a generation of magnetic fields coming from this hydrodynamical turbulence. And there are also other mechanisms that can generate magnetic fields and that can produce helicity that I'm also going to skip quickly due to time constraints, and I'm going to go now in the magnetohydrodynamic description. So we consider the plasma right after the electroweak phase transition. So we consider that the phase transition has already occurred, and that we are modeling the resulting magnetic or velocity fields that have been generated and their coupling in order to compute the subsequent gravitational wave generation. Therefore, we consider an ultra-relativistic equation of state for the primordial plasma, and we consider an isotropic and homogeneous universe such that it is expanding following the Friedmann-Lemaitre-Robertson-Walker model. So on one hand, we have contributions into the stress energy tensor that are coming from fluid motions with the ultra-relativistic equation of state and considering relativistic velocities. And we also have contributions coming from the magnetic fields, which are given by the Faraday tensor after assuming that we don't have electric fields due to the high conductivity of the universe. So once that we have the contributions from magnetic and velocity fields, we can derive the conservation laws in the expanding universe after appropriately defining some co-moving and normalized variables that they could be considered expanding with the universe. And therefore, we can derive some equations that are similar to ordinary magnetohydrodynamics that were derived in this paper by my collaborators, Axel Brandenburg and others. And these are the equations that then we're solving within the pencil code, where the terms in red are the ones that we need to add due to the relativistic considerations with respect to ordinary MHD. So now going into the generation of gravitational waves, we assume that we have an isotropic and homogeneous universe, and that there are tensor mode perturbations above this metric tensor given by the strings Hij. Therefore, after appropriately scaling Hij and using comoving and spatial coordinates and conformal time, we can derive the gravitational wave equation in its simplified form, where the damping term ends up being 0 during the radiation-dominated epoch, since we have a linear evolution of the scale factor. Therefore, we can further normalize this, and this is a technical aspect. This is the equation that we end up solving within the pencil code, and the details are explained in this journal paper. And the point from this is that we can actually apply these to different energy scales during the early universe, for example, to the electroweak phase transition or to the QCD phase transition, if we are appropriately modeling what is the anisotropic stresses that are generating the gravitational waves. As Chiara was explaining, in our case, we are sourcing the gravitational waves from the anisotropic stresses that are directly computed from the dynamical evolution of the magnetic and velocity fields. So I'm going to go into the results. This is similar to the talk by Chiara, where they were studying the generation of hydrodynamic turbulence by assuming an initial velocity field. In our case, we assume as the initial condition a magnetic field that is already turbulent, and that has some, in this case, we are considering that it has some fractional magnetic helicity given by this parameter sigma that I will explain in a moment, and that it has a smooth broken power law, such that in the lower scales, such in larger scales, we have a Bachelor spectrum, which is due to the causality and divergence of the magnetic field. So it follows k to the 4th power. And in the inertial range, we consider a Kolmogorov spectrum. So it follows like k to the -5/3. So this is the final expression of this smooth broken power law. And here we are adding this term, which depends on sigma, in order to give a magnetic field that has some fractional helicity. So we conduct numerical simulations, starting with this initial magnetic field, which is already a stochastic magnetic field which developed turbulence. And we impose the amplitude of this magnetic field such that the total magnetic energy density doesn't go above 10% of the radiation energy density given by, as I mentioned before, the Big Bang nucleosynthesis limit. And we impose the spectral peak to be at some fraction of the Hubble scale. In this case, I'm going to show some simulations where we're considering the spectral peak of the magnetic field, or the characteristic scale of the magnetic field, is about 100 of the Hubble scale. Therefore, okay, yeah, so this is some coming from the numerical simulation. We start with this initial magnetic field, as I was explaining. This is the spectrum of the magnetic field. And the generation of the final gravitational wave spectrum looks like this. We observe a flat spectrum in the subinertial range at a peak that is about twice the peak of the magnetic field, and then a similar to Kolmogorov, proportional to 1/k² with respect to Kolmogorov spectrum in the inertial range. This is different to what was expected initially from previous analytical estimations, where we were expecting something proportional to k to the 2nd power. And we actually observed that at very initial times, our initial time of the simulation is 1. So, and this is in normalized units, so this represents 1 Hubble time. So at 10 to the -5 Hubble times, we actually observe this k to the 2nd power approximately, that ends up developing in this flat spectrum after some time, after a time that is approximately 1/k star. So 1/10 to the 3 in this case for scales that are approximately at 2 pi times 100 for 100 of the Hubble scale being the characteristic scale of the magnetic field. There's still further investigation on understanding this k to the flat spectrum. It's still not well understood. And if we scale these results into the electron-wave phase transition, and we can compute the final gravitational wave spectrum that we would be observing at the present time, and compare that to the sensitivity by LISA. So here, these are the results of simulations where we are considering different parameters of the fractional magnetic helicity. So from fully helical to almost non-helical, and we can see that there is not a big impact in the final spectrum of gravitational waves. And if we take a total energy density of approximately 10% of the radiation energy density, therefore we obtain signals that would be observable by LISA. This could be the power law sensitivity of LISA for a signal to noise ratio of 10 after 4 years of observation. So this, however, is not, it is an assumption that we already have an initial magnetic field, and a way in order to model how would be the generation of this magnetic field. How we do it, since we're not coupling our equations to any scalar evolution of the scalar fields or to any magnetogenesis scenario, what we're actually doing is we try to model this generation by adding a forcing term into the induction equation, which was mentioned previously in Chiara's talk. So in order to do that, we consider a very short duration, approximately 10% of 1 Hubble time, where we switch on this forcing term. And this forcing term is a quasi-monochromatic forcing, which is around the spectral peak. So we're forcing approximately in a bandwidth around the spectral peak with a forcing term that also has some fractional helicity. And this is the technical details I'll explain in these papers. But so for you to... Yes?
You have 5 minutes left.
Okay, I'll go quickly over this. So this is, for example, how this initial magnetic field, it peaks at very initial times around this scale. We start with a non-turbulent field, and then we can see that after forcing it ends up developing a turbulent spectrum, similar to what we were observing with some differences. So, for example, in this case, after 10%, after 1%, we switch off the forcing term, and we see that it still develops this approximately. This is not Kolmogorov; it's a little bit steeper than Kolmogorov and a similar spectrum. That we still have some remainings from this spike on the energy scale of the magnetic field. So these are the resulting spectra for gravitational waves compared to acoustic turbulence, which is actually more efficient for the same amount of energy density. And this is its effect on helicity. We can see that there is an improvement an enhancement in the generation of gravitational waves. And I will skip this part and I will go into the polarization. So we expect that helical magnetic fields, they will be inducing circularly polarized gravitational waves. And we can define the ratio between this antisymmetric spectrum to the energy density, such that and we computed in this previous paper the polarization of kinetic turbulence versus magnetic turbulence. And in the case of magnetic turbulence, we can actually see that there is a helical inverse cascading around the peak. So we can actually observe and predict from these numerical simulations what is going to be the spectrum of the degree of circular polarization. So these are some new results that we have just published in this paper that I also won't have much time, but just to mention that these we are actually studying if they could be detectable by LISA. It was proposed that the LISA's dipole response function could allow to detect polarization. In our case, this is not enough, but it was also proposed that we can actually cross-correlate if we have in the future two space-based detectors in working, we can actually cross-correlate their data in order to detect polarization. And in that case, these magnetic fields and their polarization, it could actually be detectable in the case where the magnetic field is initially driven with a signal-to-noise ratio above 10, which is plotted in this case. So yeah, these are my conclusions. So we have implemented in the Pencil code a model in order to solve gravitational wave equation, which allows us to couple these to magnetohydrodynamic turbulence, and to compute therefore the background, the stochastic backgrounds of gravitational waves. The gravitational wave equation is scaled such that we can is normalized such that we can scale it to the different epochs where we expect hydrodynamic or magnetic fields to be generated during the early universe, as long as the equations are valid. And we can also couple these to other type of physics like chiral MHD, or we can only consider kinetic or magnetic fields, which hasn't still been, there's still a lot to do in this sense. So yeah, therefore these conclusions are that we might be able to detect such signals and then get information from the on one hand from the first order phase transitions, and on the other hand also from the generation mechanisms, the mechanisms of generation of the primordial magnetic fields. So with this, I conclude my talk. Thank you very much, and let me know if you have any questions now, or just you can send me an email, or we can discuss them in the panel discussion. Thank you very much.
Thanks for the nice overview on this topic. Do we have questions, comments? I don't see. Maybe I can start with, because the results, how much does it depend on the initial conditions? And is there any way to sort of derive those initial conditions from, I don't know, first principles or simulations or anything?
Yeah, so at the moment, we're just considering that the initial magnetic field or velocity field is injected in some characteristic scale, and it has some amplitude. So it depends only on these two parameters that then one needs to relate those to the parameters from first principles from the phase transition, which is something that we need to do yet.
There's a question from Tenmei.
Hi, thanks for the nice talk. One question I had was if there's a sort of physical understanding for why magnetic field helicity is tied to gravitational wave polarization. I mean, exactly what is happening? I mean, you have some twisted, like corkscrew type magnetic field, and so what does it do that it produces polarized gravitational waves?
So I don't have a strong physical intuition on why is that. I did some numerical experiments and also some analytical calculations to show that for very simple cases, and that was done that was showed previously in a paper by Tina Kaknashvili in 2005. This relation between that we expect this, and we did this in this paper that I was showing that is now in the archive for a very simple analytical case to show that. But yeah, I'm not sure if to give a physical argument for that.
All right, thank you.
Thank you.
Are there any other questions for Roberto? I don't see any more hands, so maybe we should end the session here, and I'd like to thank all the speakers of today for their very interesting talks, and I'll hand it back to the organizers.
Okay, thank you for the nice session, and we request all the speakers to be present during the discussion session. So now we take 5 minutes break. We start at 6:19 Central European time.